In the previous module, we saw how to model simple transition systems in NuSMV. In this module, we will see how hardware circuits can be described in the tool NuSMV. There are three parts to this module. In the first part, we will see a simple circuit. In the second and the third parts, we will see more interesting circuits. Consider the circuit that we saw in Unit 1. There are two inputs, X and R. The output is determined as NOT of XOR of X, R. The next value of the register or the next value of the input R is determined as XOR of X and R. The next value of X is non-deterministic. It could be anything. This is clearly described in this transition system. The initial value of R is assumed to be 0. The initial value of X could be either 0 or 1. Once the value of X and R are given, the value of Y gets determined. This gives us 4 states. Let us now try to describe this circuit using NuSMV. As usual, it starts with a module main. There are two variables, X and R. Both of them are of the Boolean type. These are the inputs. The initial value of the variable R is false. There are two things now. We need to define the next value of R and we need to assign the value Y to be not of XOR of X, R. Note that there is a difference between these two. This says that once I have X and R, the next value of R is XOR of X, R. So there is a unit delay for the next value. However, once I get X and R, immediately the value of Y is not of XOR of X, R. For the value of Y, there is no delay. How do we describe this? Here we say that next of R is X XOR R. This is fine. What about Y? We cannot say next of Y is not of XOR of X, R because once the value of X and R are given, the value of Y is determined by the current values of X and R. To model such things, there is a keyword define. This says that the value of Y would depend on the current value of X and R as follows. It is given as not of X XOR R. We do not have to separately declare the variable Y in the var block. We can directly write Y to be not of X XOR R. This variable does not play a part in determining the number of states. The number of states is going to be determined by the variables here. Since X and R are Boolean, there are two choices for X, two choices for R. Hence the number of states is going to be 4. Let us now see a demo of this. I have written the code in the file circuit-demo1.smv. Let's get into the interactive mode. You could directly give the name of the file in the command for the interactive mode. So you can write NuSMV-int circuit-demo1.smv. If you remember, we used to write read model, flatten hierarchy, encode variables, and build model. However, there seems to be a simple command go which will do all this for us. Let us now print the set of reachable states. Print reachable states minus v. There are 4 states given by x equal to true, r equal to true, x equal to true, r equal to false, x equal to false, r equal to true, x equal to false, r equal to false. As you see, the states are determined only by the variables in the var block. Let us now simulate this transition system. We pick the initial state, rather an initial state. There are two states, one with x equal to true or false, the other one has r to be false and x to be false as well. The value of y gets determined given the values of the variables x and r. So y was not of XOR of x comma r. XOR of true and false is true, not of true is false. Here r is false, so XOR of false and false is false, not of false is true. This is as we expected. Let me take this state and simulate for say 5 steps. So we started with the state x equal to true, r equal to false and y is equal to false. The next value of r should be XOR of true and false, which is true. If you see in the available states, the value of r is true. So if r is not given here, you have to look here. So r is true. However, x could be either true or false. So that's why we get two states. Let me choose 1. Here the value of r is true. XOR of true and false is true. So r is going to be true here and x could be either true or false. So you can continue doing this. Each time we have two successor transitions. That was an example of a simple circuit. What you need to remember is the use of the keyword define. Define is useful whenever the output value is determined by the current values of the inputs. Let us now look at more examples of circuits. This is a simple NAND with two inputs. Let us now describe this very simple circuit using NuSMV. Module main. There are two variables in1 and in2. We have assumed that there is a zero delay here. That is, out is determined as not of in1 and in2 immediately with zero delay. So we use the define keyword. What is the transition system representing this circuit? There are 4 states determined by the values of the inputs. And this is in1, this is in2, this is out. Out is NAND of 0, 0, which is 1. Here NAND of 1 and 0. AND of 1 and 0 is 0 and not of 0 is 1. The only place where out is 0 is here, where AND of 1 and 1 is 1 and not of 1 is 0. We have not assigned any initial states. So all 4 of them are going to be initial. Let us simultaneously see a demo of this example in NuSMV. Here is the code. Let us start running it. Let's first get the set of reachable states. There are 4 states depending on the values of inputs in1 and in2. What are the initial states? Since we have not defined what the initial state is, any of them could be the initial state. This is what we have seen here. What are the transitions? We have not defined anything here. The assign block is completely empty. So each state can move to any of the 4 states. There are all possible transitions. Let us now see this in NuSMV. We pick, say, state 0 and now simulate for 5 steps. You will get all possible options, all possible 4 states as available, no matter whatever state you choose. This clearly shows that the transition system corresponding to this code is this. Let us now slightly complicate the code. Instead of assuming that the output comes within a 0 delay, I am now assuming that the output comes after a unit delay. So we define out in the var block. We give some initial value for the output and say that once I have my inputs in1 and in2, the next value of the output is NAND of in1 and in2. If at time t equal to 0, I have 1 and 0 as inputs. At time t equal to 1, the output would be NAND of 1 and 0, which is 1. The output at time t equal to 2 would be determined by the values of inputs at time t equal to 1 and so on. Let us now start building the transition system. Since there are 3 variables in the var block, can you guess the number of states in the transition system? It would be 2 times 2 times 2, this 8 states. Since we have said that the initial value of out is true, there are 4 initial states, the ones where out is 1. Let us now check this in the tool. Here is the code. Let us start with printing the reachable states. See, there are 8 states depending on the values of the variables in1, in2 and out. What are the initial states? There are 4 initial states. All of them have the value of the variable out to be true. If you remember, I said if the value of a variable is not written here, then we have to look at the previous state. So here, this is a state where out is true. This is a state with out equal to true. This is yet again a state with out equal to true. We have 4 initial states. What are the transitions? The transition function says that the next value of output is given by not of in1 and in2. The next value of in1 and in2 is non-deterministic. Let's start from this state. The next value of output would be NAND of 1 and 1, which is 0. There are 4 possible transitions because you just need the value of out to be 0. In1 and in2 could be any of the possibilities. Now consider this state. Here the value of in1 and in2 is 0 and 0, AND of this is 0, NAND of this is 1. This would go to states where out is 1. Similarly, for these 2 states, the successors are the ones where the out is 1. Here, it's the same. The only difference is here in this state where the value of in1 and in2 are both 1. So AND of this is 1. NAND of this is going to be 0. So this goes to all these states. Let us now check this. Let us choose the state where in1, in2 and out are all true. There were 4 possible transitions. Each of them would have out to be false. Let us choose this state. Both in1 and in2 are true, so the successors should be the same set of states. Let us check it. Yes, indeed so. If I take 2, then there will be 4 successors where the value of output is true. This is the case. So you can keep checking this. Let me now give another way of writing the same code. We are going to define a new module with the name NAND. This is possible in NuSMV. We define a module NAND with 2 inputs, in1, in2. It has one output. Under the var block, there is a variable out which is boolean. The next value of out is given by this statement. How do we use this module in the main? In the main, you define 2 variables, input1, input2, and you can call the module NAND2 of input1, input2. Here, the states are going to be determined by the values of input1, input2, and Q. Q has the variable out. Let us see how NuSMV treats this code. Here is the code where NAND is defined as a separate module. The main module calls NAND2. Let us first look at the set of states. There are 8 states. Now you see, instead of in1, in2, out, you have input 1, input 2 and Q dot out. This is going to be the same as before. There is no change, except that we have the new variable names input 1, input 2 and Q dot out. Let me quickly simulate this system. Each time we should be getting 4 possible choices. Yes, this is how it is. If both the inputs are true, then we should go to states where Q dot out should be false. Indeed so. If one of them is true, we should go to the states where Q dot out should be true. Yes, indeed so. We have seen how to use modules in NuSMV code. Modules become more useful when we reuse components. For example, in this circuit, there are 2 NAND gates connected to an XOR. Here, we will reuse the module for NAND 2 times. We define 4 variables x1, x2, y1, y2, and we will define 2 variables q1 and q2 which are of the NAND2 type. They take as input x1 and x2, q2 takes as input y1 and y2. We have assumed that there is a 0 delay for this gate. F out is going to be the output of q1 and the output of q2, which is written as q1 dot out XOR q2 dot out. This shows how useful modules can be. Here is the code where we have used the module NAND2 twice. We will do the same things as before. There are a lot of states now. Why? Because there are more variables. The variables are x1, x2, y1, y2, q1 dot out, q2 dot out. So there are 2 times 2 times 2 times 2 times 2 times 2, 2 power 6 states, which is 64. Here is another place where modules become very useful. In this circuit, the output of the first NAND gate becomes the input of the second, and the output of the second becomes the input of the first. This is a hierarchical design. How do we write this? There are two inputs X and Y which are of the Boolean type. There is a variable of type NAND2 which takes as input X and Q2 dot out. There is another NAND variable Q2 which takes as input Q1 dot out and Y. Let us now try to simulate the transition system of this circuit. Here is the code. There are two NAND2 type variables. One uses inputs X and Q2 dot out, and the other uses inputs Q1 dot out and Y. The reachable states are 16 in number because there were only 4 variables: X, Y, Q1 dot out and Q2 dot out. What is the initial state? There are 4 initial states. Firstly, both Q1 dot out and Q2 dot out are true initially. That is how we have defined. Q1 is of the NAND2 type. It has a variable out of Boolean type which is initially true. So both Q1 dot out and Q2 dot out would be true. Let us take the first state where X and Y are true and both Q1 dot out and Q2 dot out are true. The next state would be determined as follows. The next of out should be not of the two inputs. So the next of Q1 dot out would be not of X and Q2 dot out. Let's see. We have taken this. The next of Q1 dot out should be NAND of true and true, which is false. Let's try to simulate and check this. What do you expect? In the next state, Q1 dot out should be false. That's how it is. Similarly, the next of Q2 dot out should be NAND of Y and Q1 dot out, which is false as well. X and Y have no restrictions. So there are 4 states. All of them have Q1 dot out and Q2 dot out to be false. You can continue to check the transition relation. We have seen that NuSMV code can be broken down into modules. These modules can be reused conveniently. Let us now go to the next example. Here is the NuSMV code of a 3-bit counter. Our task now is to understand this code. There is a module counter cell which takes as input a variable carry in. It has a variable value which is of Boolean type. In the module main, there are 3 instantiations of module counter cell. The first one, bit 0, has a carry in of true always. Bit 1 instantiates counter cell with the carry out of bit 0. Bit 2 instantiates counter cell with the carry out of bit 1. We will slowly try to understand this code by simulating this. What are the variables in the main module? Bit 0, bit 1, bit 2. Bit 0 is of the counter cell type. What are its variables? It has variables value, carry out, and it takes in a carry in. In bit 0, carry in is true. Initially, value of bit 0 is false, and carry out is determined by the define statement. So the value of carry out is given by the current values of carry in and value, which is carry in and value 1 and 0 is 0. What about bit 1? Bit 1 is instantiated with bit 0 dot carry out. So bit 1 dot carry in is 0, which is the same as this. Bit 1 dot value is false. Bit 1 dot carry out is bit 1 dot carry in and bit 1 dot value, which is 0 and 0, which is 0. What about bit 2? Bit 2 is instantiated with bit 1 dot carry out. Bit 1 dot carry out is 0, so bit 2 dot carry in is 0. Bit 2 dot value is 0. Bit 2 dot carry out is carry in and value, which is 0. This is going to be the initial state of the transition system determined by this code. Initially, these are the values. The next set of values will be determined by the next assignment. Next of bit 0 dot value is going to be bit 0 dot value XOR bit 0 dot carry in, which is 1 XOR 0, 1. Bit 0 dot carry in is always 1 because we have instantiated bit 0 with counter cell of true. With these values, bit 0 dot carry out becomes 1 because 1 and 1 is 1. Bit 1 dot value is going to be 0 XOR 0, which is 0. Bit 1 dot carry in is the same as bit 0 dot carry out. Bit 1 dot carry out is AND of 1 and 0, which is 0. Let us come to bit 2. Bit 2 dot value is 0 XOR 0, which is 0. Bit 2 dot carry in is the same as bit 1 dot carry out. Bit 2 dot carry out is 0. You can see the values here. From 0, 0, 0, we came to 0, 0, 1. So there has been an addition of 1. What is the next step? In the next step, bit 0 dot value would be XOR of 1 and 1, which is 0. Bit 0 dot carry in is always 1. With these values, bit 0 dot carry out is 0. Bit 1 dot value is XOR of 1 and 0, which is 1. Bit 1 dot carry in is the same as bit 0 dot carry out, which is 0. And bit 1 dot carry out is AND of these two, which is 0. There is no change here. XOR of 0, 0 is 0. Bit 1 dot carry out is 0. And AND of these two is 0. Similarly, if you compute the next step, you will see that from 0, 1, 0, the values go to 0, 1, 1. And then it goes to 1, 0, 0, 1, 0, 1, 1, 1, 1, sorry, 1, 1, 0, 1, 1, 1, and 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and back to 0, 0, 0. So this code is simulating a 3-bit counter. Try to simulate this code in NuSMV as an exercise. This is one more example where the use of modules is interesting. I would like to point out an observation about this example, in particular about the use of modules in this example. This was the initial state. The state is determined by the values of the variables. These are the variables in each of the modules. The next state is determined by evaluating the next assignment in each of these modules. Each of these modules moves forward in the next state. This is how the next state is determined. This kind of a scenario where all the modules take the next transition in one step is said to be synchronous composition. All assignments to all modules occur simultaneously. All assignments to all modules will occur in the next step. We will later see another form of composition called asynchronous composition, where we can force only one of the module to take the next transition. However, here we have defined bit 0, bit 1 and bit 2 to be variables of type determined by a module definition. In such a case, all of them will change in the next step and we will get a synchronous composition. We will see more about this later in more detail. Let me now summarize what we have seen in this module. We started with the definition of a simple circuit in NuSMV. We saw the use of the keyword define. Then we moved on to hierarchical designs of circuits where the use of the module keyword was important. We finally saw an example of a 3-bit counter where we could explain the synchronous composition of modules.